I'm very happy to see you all once again through this video. In this video, we are going to see how to derive the probability density function of Fisher's t distribution. So let us go to the concept. Let psi be a standard normal variate and chi square be another independent variate which follows chi-square distribution with n degrees of freedom. Then the Fisher's t is defined as t equal to psi divided by square root of chi-square by n, which follows student t distribution with n degrees of freedom. With the probability density function of t, 1 divided by square root of n, beta of 1 by 2 comma n by 2 into 1 divided by 1 plus t square by n whole power n plus 1 by 2. So we have to prove this probability density function for this t. So you please note that t is nothing but the ratio of two random variables, psi divided by square root of chi square by n. Psi is one random variable, chi square is another random variable, n is constant. So the combination ratio of two random variables is again a random variable. So let us go to the proof. So we are given that psi is a standard normal variate. Therefore, probability function of psi, which is equal to 1 divided by square root of 2 phi e power minus psi square by 2 with the range of psi minus infinity to plus infinity. And again we are given that chi square is a random variable which follows chi square distribution with n degrees of freedom. Therefore, probability function of chi square, which is nothing but 1 divided by 2 power n by 2 gamma n by 2 e power minus chi square by 2 chi square power n by 2 minus 1 with the range of chi square is 0 to with the range 0 to infinity. Now the joint probability density function of psi and chi square. Joint PDF of psi and chi square is nothing but g of psi comma chi square. Here psi and chi squares are independent. Therefore, joint density function of psi and chi square, which is equal to product of the marginal density functions, that is product of f of psi and f of chi square. Now you substitute the probability function of psi 1 divided by square root of 2 phi into e power minus I square by 2 multiplied with probability function of chi square 1 divided by 2 power n by 2 into gamma n by 2 multiplied with e power minus chi square by 2 into chi square power n by 2 minus 1. Now let us make one transformation in order to get the probability density function of Fisher's t. So the Fisher's t transformation is t equal to psi divided by square root of chi square by n. This is one random variable. So now t is the new random variable, psi is the old random variable, chi square is the old random variable. So we must get the new random variable in terms of old random variable. So this implies psi equal to t into square root of chi square by n. So again we take u equal to chi square. So u is the new random variable, chi square is the old random variable. Therefore, the old random variable chi square, which is equal to u. This implies psi equal to t into square root of u divided by n. Now we must find the joint probability density function of new random variables, that is t and u. So which is equal to the joint density function of old random variables, that is psi and chi square with the Jacobian transformation. So now we have to find the Jacobian transformation. Jacobian transformation is nothing but determinant matrix of partial differentiation of old random variables with respect to new random variables. In the first row, we find the old random variable, differentiate the old random variables with respect to new random variables. So dou psi with respect to t, then dou psi with respect to u. So which is equal to differentiation of psi with respect to t, which gives, when you differentiate this one, which give us square root of u by n. Similarly, when you differentiate the psi with respect to u, we get 1 by 2 into t square root of, u by n whole power minus 1 by 2. Since t is a constant, u divided by n power 1 by 2. So 1 by 2 will be 1 in the multiplication, power 1 by 2 minus 1. So it will be 1 by 2 into t u by n power minus half. Then in the second row, differentiate the chi-square with respect to t. So when you differentiate the chi-square with respect to t, it will be 0. Again you differentiate the chi-square with respect to u, it will be 1. Now you find the determinant of this matrix. So upper diagonal value 0, minus lower diagonal value square root of u by n. So Jacobian transformation gives us square root of u divided by n. So now in the joint density function of t and u, you substitute new random variables in this function. And you substitute the Jacobian transformation value. So we get joint density function of t and u equal to 1 divided by square root of 2 phi. This one already it was in the previous step, into e power minus chi square by 2, e power minus psi square by 2. So minus psi square by 2 is nothing but minus t square by 2 into u by n, since we have substituted the psi value in terms of new random variable. So again multiplied with e power minus chi square by 2 in the previous step. So chi square replaced by u. Then here chi square power n by 2 minus 1, chi square replaced by u, divided by 2 power n by 2 gamma n by 2 constant term. It was as usual in the previous step, multiplied with Jacobian transformation value square root of u divided by n. Okay, so when you simplify this one, which is equal to 1 divided by square root of 2 phi 2 power n by 2 gamma n by 2 root n u power n by 2 minus 1 u power 1 by 2. This root u is nothing but u power 1 by 2 into e power minus u by 2. I take minus u by 2 as a common term, then we get 1 plus t square by n. These two exponential terms are in the product form, so we can add the powers. So that's why we have obtained this term. In the next step, again 1 divided by square root of n square root of 2 phi 2 power n by 2 gamma n by 2 as usual in the previous step. Then I simplified the u. Again u terms are in the product form, so we can add the powers. So u power n by 2 minus 1 by 2 into e power minus u by 2 into 1 plus t square by n. So now our idea is we have to find the probability density function of t from the joint density function of t and u. So if we want find the probability density function of t, then we must integrate the joint probability density function of t and u with respect to u. So we need to find the range of t as well as range of u. So t is nothing but psi divided by square root of chi square by n. Chi square range 0 to infinity, a range of psi minus infinity to plus infinity. So this is negative term as well as positive term. This is always positive term. Therefore, t will be minus infinity to plus infinity. Then again we must find the range of u. U is nothing but chi square. Chi square is 0 to infinity. Therefore, automatically u will also lies between 0 to infinity. Now differentiate the joint density function with respect to u. So we call it as g1 of t. We call it as g1 of t, which is equal to 0 to t infinity, integral 0 to infinity, joint density function of t and u with respect to u. So we take all the constants outside of the integral. So 1 by square root of n, square root of 2 phi, 2 power n by 2, gamma n by 2, integral 0 to infinity, u power n minus 1 divided by 2 into e power minus u by 2, 1 plus t square by n with respect to u. Then in the next step, again as usual the constant are same in the previous step, integral 0 to infinity. So we take some simple modification, u power n plus 1 by 2 minus 1. When you simplify n plus 1, n plus 1, when you simplify n plus 1 by 2 minus 1, it will give us n minus 1 divided by 2. Then e power minus u by 2, 1 plus t square by n into du as usual in the previous step. So this complete integral in the form of integral 0 to infinity e power minus ax x power m minus 1 dx, which is equal to gamma m divided by a power m. This is gamma integral. Already we know this result. This complete integral in the form of gamma integral. Therefore, g1 of t equal to 1 by root n square root of 2 phi 2 power n by 2 into gamma n by 2 as usual in the previous step into gamma m. You note this, gamma m is nothing but gamma n plus 1 by 2. Gamma m is nothing but gamma n plus 1 by 2 divided by a is nothing but 1 by 2 into 1 plus t square by n whole power m. So this is nothing but a. This is nothing but m. So a power m. This is gamma m. So the complete integral can be written in the form of gamma integral. So this is the result. Now again we simplified this one. So 1 by root n 2 power n plus 1 by 2 root 2 phi gamma n by 2. This 2 power n by n plus 1 by 2 we obtained from root 2, that is 2 power 1 by 2 multiplied with 2 power n by 2. So 2 power n plus 1 by 2. So remaining terms are as usual in the previous step. So gamma n plus 1 by 2 into 2 power. This 2 power n plus 1 by 2 can be taken to the numerator. So 2 power n plus 1 by 2. The remaining denominator as usual in the previous step. So when you simplified all these things, so gamma n plus 1 by 2 divided by square root of n gamma 1 by 2. Gamma 1 by 2 is nothing but root 5. Root 5 can be written as gamma 1 by 2. Then multiply with gamma 2n by 2. Multiplied with 1 divided by 1 plus t square by n whole power n plus 1 by 2. So this gamma n plus 1 by 2, gamma n plus 1 by 2 divided by gamma 1 by 2 into gamma n by 2 is nothing but 1 over beta of 1 by 2 comma n by 2 multiplied with 1 divided by 1 plus t square by n power n plus 1 by 2. So the range of t already we obtained minus infinity to plus infinity. Therefore, the probability density function of t is nothing but f of t equal to 1 divided by square root of n beta of 1 by 2 comma n by 2 into 1 divided by 1 plus t square by n whole power n plus 1 by 2. So we have derived the probability density function of Fisher t. With this we stop this video. I hope you all that You may understand this concept.